So, good afternoon, everyone. We're here today from Penn State. We are Team FrequEnergy, also known as Belarus.
All right, so basically what we wanted to do is we wanted to develop a solution that was basically optimized your energy consumption in your house or your small business or your medium-sized business. So by implementing all of these different types of green technology that we have, so batteries and solar cells, we wanted to better use those to your house's advantage and basically gain a better smart grid. So we'll talk a little bit more about the different sort of methods of approach. That's my website. So we have this website, and basically what we wanted to do. All right. So we have this web-enabled tool that lets you monitor real-time data that we simulated, and we also have simulations from this place and also the local little house. And through that, we're able to generate all these different data, pathways, and they basically better estimate how you're using data, and then how we can sell and basically stabilize the grid. So there's two main concepts here. There's the stabilization of the grid. So does anyone know about frequency, like domain response and those types of things, where you provide the service that the grid might need some energy, and you provide that energy. So it's basically based on frequency response. So if we have 110 volts, 60 hertz. If it starts dropping below 59.5 hertz, then they want you to supply energy onto the grid to stabilize that need until they can get a big power plant, et cetera, to respond. And so with batteries, you're able to do that really quickly. And then the same case goes if it goes to 60.5 hertz, you're going to drain power from the grid. But usually when you do one of those services, you can't actually incorporate that with selling and buying energy that they do a lot in California and here, where you get a variable rate throughout the day. So at night, energy is cheaper to produce because they need less energy. And so people come in and they bid at a lower rate. And so if you have a variable rate, you can buy energy at 8 cents a kilowatt hour, versus 14 cents in the day. So I'm going to go in and just view. So here, if I log in to the account. So this is our main dashboard. This has basically energy data from the local house and grid, the name of it. GridStar, yeah, exactly, GridStar. And this basically has it over a several-month period. We're using that to better analyze. And Chris and Kenny are going to talk about that a little bit more. We also have an estimator app, and one of the cool things is a real-time data application. And so for this, we're actually able to view our simulated battery, which is at 75% right now, and then simulated solar cell, which is at 37%, and that's all connected to basically a Raspberry Pi, which you can control and enable. And so if you turn on one of the switches there, you'll see that that corresponds to turning on basically your. As soon as it turns on.
I think it turned itself off when we were sitting here.
Okay, so if you. So basically, that corresponds to that Arduino, and you can see the real-time data coming from the top. So the solar panels are on, as an example here, and you can see the little LED there corresponds to AC unit that you would have in your house. And so, yeah, you can see that the solar cells are going to go down, and then we also simulate grid, etc. So you can easily connect this to those systems and monitor your house. I mean, we obviously can't because it's dangerous, and we couldn't do that over the span of 24 hours here. But then you can also see the batteries charging and all of these different graphics here. And so, do you want to talk about?
Yeah, sure thing. So, given this connectedness and sort of building out our own sensor system, through a RESTful API and things like that, with a little bit of a dashboard, and then a more complex dashboard on the front end there. We also did a little bit of work sort of on a data science end, and with that idea of partitioning out part of your battery to be used for meeting the frequency demands of the grid, and also leaving a part of your battery to buy and sell energy. one thing we were interested in doing was we actually got the data set from the greenhouse, which I also forget the name of, but we tried to use that data to predict for the next hour, given the data you have at this hour, and given some of the temperature data and the data from the previous time history, what the demand of the grid would be in the given next hour, as thus you could make sure that you had the right amount of frequency distribution or that enough in your battery partitioned for that. So we did some simple machine learning. We actually used a basic neural network of perceptrons, and we took all of the past historic data and things like that, and we were able to predict for the next hour the demand in the grid up to about 75% accuracy. So it's not super high, but considering the limited data set we had, it's actually decently high. And considering if you were just using a baseline or something, you'd be much above that. And then we also did a second machine learning algorithm looking at when the optimal time to buy and sell energy was at. So this is just kind of a more basic decision tree, and a lot of it's actually just based off the simple concept that at night, a lot of times power is cheaper, and during the day, power is more expensive. So given these two models, we were able to determine when the cheapest time to buy energy is and when the best time to sell it is. And then we were also able to determine, based on the data at a given moment in the past, what the demand of the grid would be in the next given hour. And the idea here was, again, that if you have maybe a 10 kilowatt battery in your house hooked up to your solar system, if you knew what the demand was going to be, and if you knew that for the rest of the day you weren't really going to have a large demand, you could actually switch the purpose of that battery from meeting that frequency distribution demand, and you could use it to store energy that you can then buy and sell. So it sort of lets you get additional revenue out of your battery, and when you look at putting in maybe a 15-year investment into a battery, it could maybe bring your return on investment down a few years. So a lot of that was based in kind of some machine learning and a simple perceptron model and some more classification. So, and then it ties in kind of nicely with the real-time dashboard, because if you put your house on the grid with that dashboard, you can use a lot of that data then with some more advanced analytics to get good return on the battery to optimize your home, and also just to have a cool dashboard and make it more connected.
Right, so this is kind of just in general what we use to inspect our data, start generating some models. I was actually introduced by Chris to a program called Weka, right, Weka. Pretty nifty, it's a lot easier to use, a lot user-friendly than MATLAB, but I still use MATLAB because it's just my bread and butter. So we use MATLAB and Weka a lot to kind of get an idea for what is going on with your data, finding out that a lot of it is not linearly separable, which is what you want when you're looking to either classify data or generate some sort of probability distribution from it. And with that, then you have some large, awesome classification rate with that. So one of our, like he mentioned before, we were able to focus on two models. Obviously, the ultimate goal was to have this overlaying system that would control your power infrastructure. But due to time, we weren't able to get to that. We kind of started to focus more on the prediction side of things and the machine learning, and that proved to be quite a task in itself. So what we did was one of the models was able to kind of predict based on your current time and your current load whether or not that current time and that current load was going to be the last discharge you would see, right? So if you're done discharging for the day and if you met your quota for frequency regulation, then you want to sell immediately because supposedly at that time, that's when the highest point is you can sell past your discharge point. We didn't see great classification rates. Obviously, like I said, everything wasn't that linearly separable, so we couldn't use linear regression, couldn't use easy things like that. So we opted to go with Weka's it's like multi-layer perceptrons, so it's kind of like a neural network of sorts. For the first model, we got a 68% classification rate, not that great, it's decent, and then for the other one below, we got 75%. So ultimately, it'd be great to implement this into an algorithm which will control your power system infrastructure, but that's something definitely for the future.
Yeah, so given that that's kind of the bulk of our project, looking at kind of the dashboard again and looking at sort of taking a unique spin on the predictive side and trying to optimize maybe what you can do with the battery, especially as you start looking at things like the Tesla will come out and people's ability to plug in their electric car to be a battery at night and things like that. So I'd be happy to answer any questions if anyone has any at this time, the judges.
Judges, questions?
I do. And maybe I just didn't pick up on this. You mentioned about making a decision on selling do you see that becoming part of the total system from an automated perspective, or is this something that you manual decision points, or how do you see that as far? Great.
You probably see it on the automated side. So the idea here is like when the battery in the house right now, since they are locked into the frequency distribution, they're contractually like obligated to always be on demand in case there's a need for that, right? So if you can predict whether there will or won't be a need, and you know there's not going to be a need, you can then use it to sell. And then the second model we built actually determines during the day and based on like the inputs of real time, when's going to be the best time to sell. So if you did it automated, you could probably get the biggest return.
And I guess what we didn't mention is that you get, it's like an hourly constant rate if you meet your quota for frequency regulation. So it's, even if you're not discharging at that point, you're being constantly, you're making fixes so many dollars per hour.
Yeah, so based on like our estimates, we used a Tesla wall charger to basically base it off of battery cell. And so that was around 3.3 kilowatts is the power consumption that it can basically down and up. So that's what you get paid for that frequency response. Then it has a 10 kilowatt for the 3500 like kilowatt hour battery that you're basically able to charge and discharge. So as long as you stay within your bounds and you're certain that you're still able to meet your frequency response curves, then you're basically able to still buy all the way up to like 95% and sell all the way down to 5%. And then basically, it's not double, but get like 1.8 times, your amount of basically revenue for implementing something pretty simple with it. So it's, maximizing both sides.
And being entirely software-based, right, and being entirely automated, you can pretty much just install this in your firmware or something like that, or bolt it on top and get better revenue out of your battery.
Install this in your house, go to work while you're doing something else, it's just making money for you.
So you do run into a problem where you are using the battery more extensively, but you end up getting, instead of a 15-year return on investment for a lot of these types of batteries, you can get it down to 10 years or so with this system. So that's at least what we're predicting.
So is this ready to go on tomorrow?
Yeah, actually, yeah. So
where will you? It's going to go on the website for.
It's actually
the models are open source, so there'd be some hardware problems, but
that's
a day or two to iron those out.
Yeah, basically, all of the firmware. There's like an API, and you can basically, establish this. It's actually really easy. I can go into a little bit more detail about how it works. We have an Amazon EC2 instance that we're running here, and then we actually connect to a Dynamo database. And so this basically Raspberry Pi here connects to Wi-Fi, and it actually has automatic software updates as well. So every midnight, it basically updates, or whenever you restart the device, it also updates. And basically from that, it basically syncs this text file to an S3 bucket at night, and then you can access that data in the long term, and then you can view the data in real time on this like sort of dashboard, and that's just from our Dynamo database. So it's pretty simple, and then basically from there, you can it's all in Python, so you can write in pretty easy communication with whatever sensors you want in their house. So if it's I2C or anything like that, or even over Ethernet, you can communicate. And we wanted to create a dashboard that's really similar to what they had already over there, that they spend thousands and thousands of dollars on. This is actually all modular, so you can actually move these things around. So if you have more sensors that you want to add on, you can actually just take an image, and it's basically like a drag and drop type of system, and then it syncs up with our other stuff. And we have a little bit to do there to make it like super user friendly, to make it all this drag and drop. But at least this setup is pretty simple, and you'll notice that some of those lines will turn on and off depending on how they're working.
We have real sensors, so we just made ourselves little kind of fake sensors to use and get real-time data from. But this is the photodiode, so it does actually.
But, yeah.
So.
Since it's all open source and pretty commodity hardware, you can bolt it on something tomorrow. Sure.
Yeah.
And this website's live. So
Yeah.
You can build all this weekend?
Yeah.
Yeah. All of it.
Yeah, it's actually it's a lot of work. But yeah, if anyone's familiar with Node.js and those types of things, it ends up taking a while, and it's we have Express running on Node.js.
Other questions from the judges? Ricardo, any questions?
So you mentioned about about like prediction of 1 hour. Is this it is enough?
Yeah. I mean, it's pretty accurate. Ideally, we'd actually run the estimates at a very short time span. But our data that we got was only for 5-minute time spans. But what's nice is that our data here, if you install this type of device and start monitoring, you can use that data to better predict as well. And we actually gather data every half a second on this. So you actually get pretty large data sets. But I mean, it's pretty easy to shift through big data sets. So,
Great.
yeah, you'd be able to bring those errors down much smaller if you had, more accurate data sets. And something that we really wanted to do was incorporate weather prediction and other prediction methods. So for example, when you have a stadium that turns on, that's in particular, like it uses a lot of power, and you want to be able to meet that frequency. So maybe on some day that you have like a football game, you don't want to go down all the way to 5% on the off-peak time. It's also Sunday, but so maybe a better example would be like a baseball game, where you don't want to go down too low because you might have to, fluctuate around a lot.
And it would also take into consideration with your solar panels what the weather's going to be, so how much sun you're going to get that day. It'll estimate how much
So a lot of those
energy you
algorithms.
can expect to get from your solar panel.
Yeah.
Any other questions?
Yeah, after you Manchester, I had a powerless night already a couple of times. So
Yeah.
but thank you very much.
So any other questions from the judges? All right, thank you, team.